12,000 miles above your head, a chunk of rock screamed past Earth faster than a rifle bullet, and almost nobody saw it coming. On August 12th, an asteroid slipped by closer than anything tracked this year, gliding inside the ring where our own satellites circle the planet. Today we ride that flyby, meet the telescopes racing to catch rocks before they arrive, and creep toward an even bigger encounter, already marked on astronomers' calendars 3 years from now. If close calls from space keep you looking up, tap like and subscribe. It helps this story reach more people like you. Space looks calm from down here, but it is crowded with rocks that pass closer than you would ever guess. Buckle in, we begin. It is just after midnight in the Canary Islands, and a camera bolted to a mountaintop telescope catches a faint smudge of light crawling across the stars. Nobody in the room raises their voice. Nobody rushes for the phone. The smudge gets logged, checked, and logged again, and within hours the world has a new number to worry about. That smudge is a rock called 2026 PC6, and it is about to do something no other asteroid has done all year. On August 12th, this rock skims past Earth at a height of about 14,000 kilometers, which is roughly 8,700 miles. Picture the distance from New York to Los Angeles, then almost 3 times that again, straight up into the sky. That sounds huge, until you remember this rock started its journey from somewhere between Mars and Jupiter, drifting for years through a void where distances are measured in millions of miles. Getting this close to a planet is like threading a needle from across a football field, blindfolded, while the needle is also moving. Here is the number that makes astronomers sit up. Out of every asteroid tracked passing near Earth in 2026, this rock wins on one measurement alone: sheer closeness. More than 100 rocks have swept inside the Moon's orbit this year, and this one beats every single one of them for proximity. It slides in nearer to Earth than the ring of satellites that beam your weather forecasts and your phone calls down from orbit. Nothing about this rock looks dramatic. It is small, somewhere between 20 and 50 feet across, roughly the size of a delivery truck with no tail and no glow. Step outside that night and look up, and you would see nothing at all. Yet for a few brief minutes, this quiet piece of rubble becomes the closest object of its kind to graze our planet in 2026. Scientists felt thrilled watching it happen. A close pass like this is a free science experiment, a chance to watch a wandering piece of the solar system without launching a single rocket. Telescopes around the world turn toward it, timing its arrival down to the second, tracking its path down to the kilometre. For a small rock with a forgettable name, it earned itself a night of global attention. But here is the part that should make you lean in closer. This rock was found only about a day before it arrived. 23 hours, to be exact, stood between the moment a telescope first noticed it and the moment it screamed past our planet. A rock big enough to shatter windows for miles around, moving fast enough to cross the distance from Los Angeles to New York in under 3 minutes, and humanity had less than a day of warning. That gap between discovery and arrival is the normal, uncomfortable truth about rocks this size, and it happens far more often than most people realize. Every week, somewhere on Earth, an observatory spots a new rock only days, sometimes only hours, before it slips past our planet. Most of these rocks are small enough to burn up long before reaching the ground, but every single one of them starts the same way, as an unknown dot of light, until a telescope on a quiet mountain looks up at exactly the right moment. Once you understand why these rocks stay hidden until the last possible hour, you will never look at the night sky the same way again. Picture the sky above your head as a set of invisible rings, stacked one inside another like a giant target. The closest ring holds the International Space Station, floating about 250 miles up, so close that astronauts can watch thunderstorms roll across entire countries in seconds. Farther out sits a thicker ring packed with GPS satellites, the ones that tell your phone exactly where you're standing. And far beyond that, about 22,000 miles up, sits the outermost ring, home to the weather and communication satellites that keep the modern world talking to itself. This asteroid did something almost none of its cousins manage. It threaded straight through that middle ring, passing at a height of about 8,700 miles, closer to Earth than most of the satellites beaming down your weather forecast, and even closer than a good number of your GPS signals. For a few minutes, a wild, untracked piece of rock was flying through the same neighborhood as billions of dollars of orbiting technology, and nobody controlling those satellites got a vote in the matter. Here is where the size of that gap gets easier to picture. Stack about 3,000 Mount Everests on top of each other, and you would just about reach the height where this rock passed by. Now imagine something the size of a delivery truck slicing through that entire stack in under 2 seconds, because that is roughly how fast it was moving relative to Earth. Space agencies build satellites with extreme care, mapping their exact paths for years in advance. This rock followed no such plan. It simply fell through the gap, guided only by gravity and sheer luck. Satellite operators were never in real danger, and here is why. The volume of space inside that outer ring is almost impossible to picture, stretching across an area far larger than the entire surface of Earth. A single truck-sized rock crossing through that emptiness is closer to a single raindrop falling through an empty football stadium than to a genuine collision risk. Even with thousands of satellites in orbit, the actual odds of two objects meeting in that much open space are tiny. Still, every time a rock like this slips through, the people who track satellites for a living pay very close attention, because the math only has to go wrong once, and a strike at those speeds could knock out a satellite instantly. Think about how many services depend quietly on that outer ring. Phone calls, live sports broadcasts, and storm warnings before a hurricane makes landfall all bounce off satellites hanging in that same space this rock just crossed. The pass came and went in silence, and every satellite kept doing its job exactly as planned. What makes this pass remarkable is the reminder it leaves behind, that our carefully mapped, carefully controlled zone around Earth still has room for surprises. We track thousands of satellites down to the inch, yet a rock the size of a delivery truck can wander through that same space almost completely unnoticed until the final hours. That question, how something can stay hidden until the very last moment, sits at the center of everything you're about to learn. The real story of this rock is how close it came, without anyone knowing it was coming at all, and that mystery starts on a mountaintop, with a telescope and a single flicker of light. High on a mountain in the Canary Islands, off the coast of northwest Africa, a robotic telescope opens its shutter the moment the sun goes down. It does not sleep. It does not take breaks. Every clear night it sweeps the same patch of sky again and again, comparing each new image against the last, hunting for anything that moved. This particular night, something moved. The telescope belongs to a system called ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, and this one sits at Tidy Observatory on the island of Tenerife. At around 1 in the morning on August 11th, its software flagged a faint point of light shifting slightly against the fixed background of stars. A computer algorithm made the first guess. A human astronomer confirmed it minutes later. Within the hour, the discovery was uploaded to a shared international database, where telescopes across the planet could pick up the trail. Here is the part that turns routine detection into a race against the clock. From that very first spot of light to the moment the rock made its closest pass by Earth, less than a full day went by. 23 hours and 30 minutes, to use the exact number logged by astronomers. In that short window, scientists had to confirm the object was real, calculate its speed, map its path, and determine with confidence that it posed no danger, all before the rock arrived. Think of it like spotting a car speeding toward an intersection from 3 blocks away and having to calculate its exact path, speed, and destination before it reaches you. Except the intersection is the size of a planet and the car is moving faster than anything built by humans. Astronomers pulled it off with hours to spare, but barely. More than 100 separate observations poured in from telescopes around the globe during that short window, each one refining the rock's path a little further. Every new data point tightened the picture, shrinking the uncertainty from a wide, blurry cone of possible locations down to a single, confident line. By the time the rock made its closest approach, scientists knew its position to within a few miles, an extraordinary feat for an object discovered less than a day earlier. This kind of teamwork happens almost entirely out of public view. A discovery gets logged on one continent, confirming images arrive from another within the hour. A calculation gets checked by a scientist half a world away before most people have finished breakfast. There is no single command center running the show, no giant control room from a movie. Instead, there is a loose global web of observatories, universities, and space agencies, all trusting the same shared data, all racing the same invisible clock. What makes this story worth telling is the sheer speed of human teamwork on display. Telescopes on different continents, run by different countries, all quietly working together within hours to solve the same puzzle. No press conference, no emergency meeting, just data, shared freely, moving faster than the rock itself. But this raises an uncomfortable question. If a truck-sized rock can appear from nowhere and reach Earth in under a day, how many rocks just like it are out there right now, drifting unseen, waiting for their own telescope to finally notice them? Imagine holding a piece of coal at arm's length in a dark room and asking someone across the street to spot it using only their eyes. That is close to the challenge facing every telescope hunting for rocks like this one. Most asteroids are not bright, shining objects. They're dark, dusty, and about as reflective as a lump of charcoal, which means they only become visible when sunlight catches them at just the right angle, at just the right distance. This particular rock measured somewhere between 20 and 50 feet across, small enough to fit on a city street with room to spare, and dark enough to swallow most of the light that hit it. For weeks or months before its flyby, it was likely drifting through space completely unnoticed, a tiny dark speck lost against a black background that stretches for trillions of miles in every direction. Telescopes were not failing to look. There was simply nothing bright enough to see. Everything changed as the rock swung closer to Earth. Sunlight bounced harder off its surface. Its apparent brightness climbed night after night, the way a car's headlights seem to brighten as it drives toward you from far down a dark road. Astronomers track this brightening using a scale called magnitude, where lower numbers mean brighter objects. In the days before its closest approach, this rock's brightness surged, climbing fast enough that telescopes finally had a fighting chance to catch it before it arrived. Even then, catching it required precise timing. Too early, and the rock stayed too faint for even powerful telescopes to separate it from the noise of distant stars and galaxies. Too late, and it would already be gone, vanishing back into the depth of the solar system before anyone confirmed what they had seen. Astronomers essentially had one narrow window, one particular night, when the rock was finally bright enough and still far enough away to give them time to react. Weather adds another layer to the challenge. A single cloudy night over the wrong observatory can erase an entire window of opportunity, forcing astronomers to rely on a global chain of telescopes scattered across different continents and time zones. If one site gets clouded out, another site somewhere else on the planet might still have a clear view of that same patch of sky, which is exactly why space agencies fund observatories in places as different as Hawaii, Chile, South Africa, and the Canary Islands. This is the uncomfortable truth about small, dark asteroids. They spend almost their entire visible lifetime as nothing more than a rumour, a faint smudge easy to mistake for a smudge on the lens or a distant, unrelated star. Only in the final days before a close pass does a rock like this reveal itself clearly enough to be tracked, named, and understood. Now stretch that same problem across the entire solar system, filled with millions of similar dark, tumbling rocks, most of them far smaller than the one that just passed Earth. Somewhere out there, right now, another one is brightening night by night, completely unnoticed, waiting for its own moment to finally step out of the dark. And the only way to catch it in time is to already know exactly how close is too close. Astronomers needed a simple way to talk about distances that make a calculator sweat, so they invented a shortcut called a lunar distance. One lunar distance equals the average gap between Earth and the Moon, about 238,000 miles. Instead of writing out long strings of numbers every time a rock passes by, scientists just say how many lunar distances separate it from us. A rock at one lunar distance is exactly as far as the Moon. A rock at half a lunar distance is halfway there. This particular rock passed at a mere 5/100ths of a lunar distance. Picture the full stretch between Earth and the Moon as a highway 238,000 miles long. Now imagine a car exiting that highway after driving only about 12,700 miles, roughly 5% of the total trip. That is how close this rock came, a tiny fraction of the way to the Moon, closer than almost every other object tracked passing Earth this year. Compare that to another headline making rock from earlier in the year, which passed at about a quarter of a lunar distance, still an impressively close call by most standards at the time. This new rock beat that distance by a wide margin, coming in nearly 5 times closer. Among more than 100 asteroids that swept within 1 lunar distance of Earth so far in 2026, none came anywhere near this close, which is exactly why this particular flyby earned the title of the year's tightest squeeze. Here is a comparison that might help it click. If the Moon sat exactly where your favourite stadium sits, this rock passed by close enough that it barely cleared the parking lot. Scientists use the lunar distance scale specifically because raw numbers in miles or kilometres can numb the brain, while a simple fraction of a familiar trip instantly tells a story. 0.053 lunar distances says this rock nearly grazed us, using a yardstick anyone can picture. Astronomers did not stumble onto this number by accident. Every new observation feeds into a model that calculates the rock's exact path, refined again and again as more data arrives. The lunar distance figure you hear reported is the end result of that process, a single clean number built from dozens of individual measurements taken by telescopes scattered across the globe. Behind that one simple fraction sits hours of careful, repeated calculation, checked and rechecked before anyone felt confident enough to publish it. Once you start measuring the sky this way, something strange happens. You realise just how crowded near-Earth space actually is. Objects pass within a single lunar distance on a regular basis throughout the year, most too small or too faint to ever make the news. This rock stood out only because it pushed that fraction closer to 0 than anything else recorded in 2026, a title it is unlikely to hold for very long. Somewhere out past the orbit of Mars, more rocks are already drifting toward their own turn at breaking this exact same record, and the only real mystery left is which one arrives first, how much warning we get before it does, and just how much closer to 0 that fraction can actually go. Strap into a car on the highway, push the pedal to 60 miles an hour, and that already feels fast enough to blur the world outside your window. Now multiply that speed by roughly 600, and you start to approach how quickly a rock like this one crosses the space near Earth. Near Earth, asteroids typically travel between 20,000 and 45,000 miles per hour relative to our planet, fast enough to make a rifle bullet look like it is standing still. A high-powered rifle bullet leaves the barrel at around 1,700 miles per hour, fast enough to cross a football field in under half a second. A commercial jet cruises at roughly 550 miles per hour. A rock like this one moves 10 to 25 times faster than that bullet, and dozens of times faster than the jet carrying passengers across the country. At those speeds, the rock could cross the entire length of the United States, coast to coast, in well under 10 minutes. Speed like this is not a choice the rock makes. It comes from billions of years spent falling through the gravity of the sun, picking up momentum the entire time, the same way a skateboarder gains speed rolling down a long steep hill. By the time a rock like this reaches Earth's neighbourhood, it has been accelerating in fits and starts for longer than humans have existed as a species. This kind of speed changes everything about how astronomers respond to a new discovery. There is no towing a rock back for a closer look, no slowing it down to buy more time. Every calculation has to happen while the object is still moving at tens of thousands of miles per hour, using nothing but light bouncing off its surface and a handful of images taken hours apart. Engineers on Earth solve equations fast enough to predict, days in advance, exactly where a speck of light moving at incredible speed will be at a precise second in the future. Radar offers one of the sharpest tools for pinning down that speed. A powerful dish on the ground sends out a burst of radio waves, waits for them to bounce off the rock, and measures exactly how long the echo takes to return. That tiny delay, often just a fraction of a second, reveals both the rock's distance and its speed with startling precision, turning a distant point of light into a set of hard, trustworthy numbers scientists can trust for years afterward. Speed also explains why a pass like this one lasts only minutes from a human perspective, even though the rock had been travelling toward this exact moment for months or years. Blink at the wrong second while watching a live stream of the flyby, and you could miss the entire closest approach. The rock does not slow down to be seen. It simply arrives, crosses through, and continues on its endless journey around the sun. And that raises a question worth sitting with. If a rock this fast can be spotted, tracked, and understood in under a day, what happens when the numbers are even less forgiving, and the warning window shrinks from a full day down to just a handful of hours, or even less time than it takes to finish watching a single video? Somewhere on Earth, at the exact moment this rock made its closest pass, people were doing completely ordinary things. Someone was walking a dog. Someone was falling asleep in front of a television. Someone was staring up at a clear night sky, seeing nothing but the usual stars, completely unaware that a truck-sized piece of the solar system had just swept by closer than most satellites. No tremor, no flash of light, no sound, just an ordinary night, exactly like any other, ending exactly the way it began. That silence makes sense once you understand what this rock actually did and did not do. It never touched Earth's atmosphere. Even at a height of about 8,700 miles, it stayed thousands of miles above the thin blanket of air that wraps our planet and makes weather, sound, and breathing possible. Without atmosphere to push against, there was no friction, no heat, no shockwave, nothing capable of reaching the ground. The rock simply sailed through empty space, changed direction slightly under Earth's gravity, and continued on its way. Compare that to what happens when a rock actually enters the atmosphere. Friction against the air builds heat fast enough to make even small rocks glow brighter than anything else in the sky, sometimes for only a few seconds before they burn apart completely. That kind of event produces real, noticeable effects, a streak of light, sometimes a sonic boom, sometimes debris scattered across the ground below. This rock produced none of that, staying far too high to ever touch the air. Distance made all the difference here. 8,700 miles sounds close when compared to the vast emptiness between planets, yet it remains more than 1,000 times higher than a commercial airplane cruising altitude. Even the International Space Station, orbiting at roughly 250 miles up, sat far closer to Earth's surface than this rock ever came. The rock passed through a zone reserved for distant satellites, nowhere near thick enough air to notice its arrival. Timing played a part too. The closest approach happened while much of the world faced away from the sun, deep in nighttime darkness, yet even skywatchers with a telescope pointed at exactly the right patch of sky needed to hunt for a small dark object hundreds of times fainter than anything visible to the naked eye. Only the observatories already tracking it captured a clear image of it slipping past. Everyone else simply went about their evening, completely unaware that this year's closest tracked flyby was happening directly overhead. This matters because it draws a clear line between two very different kinds of asteroid stories. One kind involves a rock passing by at a safe, if startling distance, generating headlines and telescope images, but nothing more. The other kind involves a rock actually entering the atmosphere, producing real, physical effects that people on the ground can see, hear, and sometimes feel. This flyby belonged firmly to the first category, a close call in the mathematical sense, calm and quiet in every practical one. But that second kind of story has happened before, and when it does, the sky itself becomes the warning, brighter than the sun for a few unforgettable seconds, loud enough to be heard hundreds of miles away. 4 mountaintops, spread across 4 different corners of the world, share one single job. Every clear night, robotic telescopes on these peaks open their eyes and scan the sky above, searching for anything that should not be there. One sits in Hawaii, one sits high in the Chilean desert, one watches from South Africa, one looks out from the Canary Islands, the very same site that caught this rock before its record-setting flyby. Together, these 4 stations form a system called the Asteroid Terrestrial Impact Last Alert System, built with one specific mission: to catch dangerous rocks before they arrive. This network works like a relay race that never stops. As Earth spins, different telescopes rotate into darkness while others rotate into daylight, meaning at almost any hour, somewhere on the planet, one of these cameras has a clear view of the night sky. A rock that slips past detection over the Pacific might still get caught hours later as it drifts into view over Africa. No single blind spot lasts forever. because the planet itself keeps turning new eyes toward the stars. This system does not work alone. Older, equally important surveys keep running alongside it, including the Catalina Sky Survey, operating telescopes on Mount Lemmon in Arizona, and another major project called Pan-STARRS, based in Hawaii. Each survey uses slightly different equipment and strategies, some built to catch faint, distant objects early, others built to catch fast-moving, close-approaching rocks in their final hours. Together, they cover gaps that any single telescope working alone would inevitably miss. Picture it like a neighborhood with several different security cameras, each pointed in a slightly different direction, each catching a slightly different angle of the same street. One camera might miss a fast-moving car speeding past at night. Another camera, positioned just right, catches it clearly. Multiply that idea across an entire planet, and you start to understand why a rock discovered in the Canary Islands can be confirmed within hours by telescopes on completely different continents. Every one of these telescopes feeds its data into a shared clearinghouse, a central database where new detections get logged, checked, and cross-referenced against everything already known about the solar system. This is the quiet machinery working behind every asteroid headline you have ever read, dozens of scientists and automated systems spread across a dozen time zones, comparing notes on a shared spreadsheet of moving dots of light. Without that shared system, each observatory would be working blind, unaware that another telescope halfway around the world had already spotted the exact same rock hours earlier. None of this technology runs itself for free. Space agencies fund these surveys specifically because a single missed detection could mean the difference between weeks of advance warning and almost none at all. Every telescope in this network exists because of one shared goal: protecting a planet that spends most of its time completely unaware of what is passing silently overhead. Yet even with 4 dedicated stations and multiple independent surveys working around the clock, this rock still slipped through undetected until less than a full day before arrival. That gap between an enormous global effort and a single day of warning raises an uncomfortable question about just how many rocks this size are still managing to sneak by completely unnoticed. Right now, while you read this sentence, another rock is somewhere between Earth and the Moon, passing by completely unnoticed. This is not a rare event reserved for headline-making moments. It is simply how the neighborhood around our planet works. So far in 2026, more than 100 separate asteroids have swept within a single lunar distance of Earth, an average of more than one every 3 days. Most of these rocks never make the news, and there is a simple reason why. The vast majority are small, some barely larger than a beach ball, others closer in size to a car or a small house. None of them come close enough, or large enough, to threaten anything on the ground below. They arrive, cross through the space near Earth, and continue on their journey around the Sun, leaving behind nothing but a data point in a scientific database that almost nobody outside of astronomy ever reads. Think about your own week. In the time it takes you to go from one Monday to the next, statistically speaking, 2 or 3 new rocks will have quietly swept past Earth within the distance of the Moon. You will not feel it, you will not see it, unless you happen to be watching the right patch of sky through a telescope at the exact right moment. Life continues exactly as normal, while a steady, invisible traffic of ancient rubble streams past our planet in the background, the same way it has for longer than anyone can truly imagine. This constant traffic is not new. It has been happening for the entire 4.5 billion year history of Earth, long before telescopes, long before humans existed to notice or worry about any of it. What changed recently is our ability to actually track it. A century ago, nearly every one of these close passes would have gone completely unrecorded, hidden simply because nobody had the tools to catch them, not because the rocks themselves were unusual or rare. Today, a global network of telescopes turns that invisible traffic into a running, searchable record. Every rock gets a name, a measured path, and an official file, even the ones too small and too harmless to ever matter beyond a line in a database. This record-setting rock earned extra attention only because it broke a specific number, proximity, not because it behaved any differently than the countless others that pass by every single week. Scientists keep a running tally of these encounters precisely because patterns matter more than any single event. A single close pass tells you almost nothing on its own. A full year of close passes, logged and compared side by side, starts to reveal something far more useful. How often truly close calls happen, how large the average rock tends to be, and whether the overall rate is climbing as detection technology keeps improving. That bigger picture only becomes visible once enough individual flybys pile up into a real, searchable history. Which raises the real question worth sitting with. If harmless rocks slip past this often without anyone on the ground even noticing, how confident can anyone truly be that every single one of them actually is harmless? And who is checking closely enough to be sure? Here is a question that sounds simple but trips up almost everyone the first time they think about it. Which matters more, how close a rock comes, or how big that rock actually is? The honest answer is that distance alone tells you almost nothing. A rock the size of a grain of sand could pass 1 mile from Earth and you would never notice. A rock the size of a mountain passing at 10 times the distance of the moon would still make headlines around the world because its size alone makes it worth watching closely. This record-setting rock earned its fame purely from proximity. At somewhere between 20 and 50 feet across, it ranks among the smaller objects astronomers track regularly, closer in scale to a delivery truck than to anything resembling a real threat. Even if this particular rock had been knocked slightly off course and entered Earth's atmosphere directly, the outcome would likely have been unremarkable. A bright streak of light burning up harmlessly, perhaps a loud boom heard by people nearby. Nothing close to a disaster. Size changes that entire equation, and it does not change it gently. Double the width of a rock, and its mass increases roughly 8 times over, since volume grows with the cube of size rather than in a straight line. A rock twice as wide as this one carries roughly 8 times the mass, and therefore roughly 8 times the energy when it eventually meets Earth's atmosphere. A rock 5 times wider carries over 100 times the mass. The bigger a rock gets, the faster the danger climbs, far faster than most people expect from picturing simple, easy math. This is exactly why astronomers care so much about measuring size accurately, sometimes even more than measuring distance. A telescope can often calculate an object's path with impressive precision within hours of discovery, yet its exact size frequently remains an educated guess, based only on how much sunlight the rock reflects back toward Earth. 2 rocks reflecting the same amount of light could be wildly different sizes, one dark and large, the other bright and small, and only follow-up observations or, in rare cases, radar can settle which one is true. Think of it like judging a car's size from a photograph taken at night, lit only by its own headlights. A bright, close headlight and a dim, distant one can look almost identical in a single image, even though the vehicles behind them are nothing alike. Astronomers face that exact puzzle every time a new rock appears, and it is one reason early size estimates often carry a wide range rather than a single confident number, sometimes stretching from 20 feet across all the way up to 50. Understanding this relationship between size and danger completely changes how you should think about every asteroid story you will ever hear. A rock passing extremely close but extremely small deserves curiosity, not concern. A much larger rock, even one passing at a far safer distance, deserves genuine attention. The record broken by this flyby was about closeness, not danger, and remembering that difference is the key to understanding everything still ahead. Because somewhere in the historical record sits a rock that combined both unmistakable size and a shockingly close call, and what happened next reshaped how an entire generation of scientists thought about the sky above them. On a freezing February morning in 2013, over the Russian city of Chelyabinsk, the sky itself seemed to catch fire. A rock roughly 66 feet across, larger than the one that just skimmed past Earth, slammed into the atmosphere at somewhere around 40,000 miles per hour. For a few brief seconds it burned brighter than the sun, so bright that people driving to work that morning saw their own shadows stretch out sharply across the snow, cast by a light source streaking silently overhead. Nobody on the ground saw this coming. Unlike this year's record-setting flyby, Tracked for nearly a full day before arrival, the Chelyabinsk rock approached from a direction almost directly in line with the sun, hidden completely inside the glare. No telescope on Earth caught so much as a glimpse of it before it arrived, and no warning of any kind reached the people below. The first anyone knew of its existence was the moment it lit up the sky above their heads. About 14 miles above the ground, the rock could no longer survive the pressure building against it, and burst apart in a massive airburst, releasing energy equivalent to roughly 30 times the force of the atomic bomb dropped on Hiroshima. All of that energy came from a rock small enough to fit inside a modest house, a sharp reminder that size alone never tells the full story, since speed and angle of entry matter just as much as raw mass. The flash came first, then a delay that must have felt endless to anyone watching, and finally the shockwave arrived. Windows across the region shattered from the force of the blast, sending broken glass flying through classrooms, offices and homes. Over 1,500 people were injured that day, the overwhelming majority from flying glass rather than from the rock itself, which never even reached the ground in one piece. Roofs partially collapsed under the pressure wave. Car alarms triggered across entire neighborhoods at once. What makes Chelyabinsk especially unsettling is the warning it never gave. A rock powerful enough to injure over 1,000 people arrived with zero advance notice, invisible until the very instant it exploded above a city of over 1 million residents. Compare that to the rock you just learned about, discovered nearly a full day ahead of its closest approach, and you start to see just how much progress detection technology has made and just how far it still has to go. The city itself recovered quickly, but the event permanently changed how seriously governments around the world treat asteroid detection. Space agencies pointed to Chelyabinsk directly when arguing for more funding, more telescopes, and faster software to catch rocks approaching from the sun's direction, the exact blind spot that let this one slip through completely unseen. Entire new detection strategies were designed specifically to close that gap, scanning twilight skies where a rock hidden by glare might finally reveal itself for a few precious minutes each day. Chelyabinsk still ranks among the largest objects recorded entering Earth's atmosphere in the modern era of tracking, yet history holds an even larger example. Over a century earlier, in a remote stretch of Siberian forest, something far bigger arrived, and the destruction it left behind still puzzles scientists today. Every single day, without exception, Earth's atmosphere absorbs a quiet bombardment from space. Tons of material rain down constantly, most of it smaller than a grain of rice, burning up so completely that nobody on the ground ever notices. This happens so routinely that scientists barely consider it newsworthy. The real question worth asking is which of these rocks actually survived the trip through the atmosphere and reached solid ground. Entry into the atmosphere is a brutal, one-sided fight between rock and air. A falling object moving tens of thousands of miles per hour slams into molecules of air that suddenly behave less like a gentle breeze and more like a solid wall. That collision generates extreme heat, sometimes exceeding several thousand degrees, hot enough to melt steel almost instantly. Most small rocks simply cannot survive that punishment. They glow brilliantly for a few seconds, streak across the sky as what most people call a shooting star, and vanish completely into dust and vapour long before reaching the ground. Size and toughness decide who wins that fight. A rock built from loose, crumbly material, similar to a dry clump of dirt, tends to shatter and disintegrate almost immediately under that kind of pressure. A denser rock, especially one containing metal, can hold together far longer, sometimes long enough to survive the entire trip through the atmosphere and land relatively intact. Once a fragment actually reaches the ground, its name officially changes. In the sky, scientists call it a meteor. On the ground, it becomes a meteorite, a small but genuine souvenir from somewhere else in the solar system. Scientists actively hunt for these fallen fragments after a major event, since each one carries chemical clues about where it formed and how old it truly is. A meteorite recovered within days of landing can reveal details impossible to learn any other way. Information about the early solar system preserved inside a rock that finished its multi-million-mile journey by landing in a farmer's field or a quiet forest clearing. Angle of approach matters just as much as material makeup. A rock diving straight down, like an arrow shot directly at the ground, spends less time in the thick, resistant lower atmosphere, and can sometimes punch through with more of its original mass intact. A rock skimming in at a shallow grazing angle spends far longer exposed to friction and heat, giving the atmosphere more time to tear it apart before it ever gets close to the surface, even if that same rock started out significantly larger than the one that dove in steeply. This is exactly why the Chelyabinsk rock exploded miles above the ground instead of leaving a massive crater. Its shallow entry angle and relatively loose internal structure meant the atmosphere had enough time and enough force to break it apart completely before it ever reached solid ground, converting nearly all of its energy into a single, sudden shock wave instead of a direct impact that would have scarred the Earth for centuries. Sometimes, though, the atmosphere loses that fight entirely, and when it does, the result carves itself permanently into the landscape, leaving behind destruction with no crater, no debris field, and for over a century, barely any explanation at all, only splintered trees stretching for miles in every direction. Picture standing outside on an ordinary morning when, without warning, the entire sky turns brighter than noon, even though the sun sits low on the horizon. That flash arrives first, instant and blinding, casting sharp shadows across the ground exactly like a camera flash the size of a city. There is no siren, no rumble, no warning sound leading up to it, only pure, sudden light where a normal sky used to be. For several long seconds afterward, nothing else happens. The rock has already finished exploding by the time that light reaches your eyes, since light travels far faster than sound. During this eerie gap, witnesses often describe a strange, held breath kind of silence, the sky slowly fading from blinding white back toward a smoky, streaked haze, while the actual force of the blast still races toward the ground far behind the light that already arrived. Then the sound catches up, and it arrives less like a single boom and more like an entire freight train slamming into a wall. This is the shockwave, a wall of compressed air pushed outward by the explosion, carrying enough force to shatter glass, rattle doors on their hinges, and in extreme cases partially collapse weaker roofs and structures. Unlike the flash, which reaches everyone within view almost instantly, the shockwave takes time to travel, meaning people farther from the blast experience the flash first and the sound and force minutes later. Ground-level effects depend heavily on how much energy the airburst released, and how high above the surface it happened. A powerful enough explosion, even one that never touches the ground directly, can still be picked up by sensitive seismic equipment normally used to detect earthquakes, registering as a genuine tremor moving through solid rock. Pressure sensors built to detect distant nuclear tests have picked up airbursts from halfway around the world, proof that the shockwave from a large enough rock can circle significant portions of the entire planet, bouncing through the atmosphere and getting detected again hours later on the opposite side of Earth. Afterward comes a strange kind of debris, usually a fine dust trail rather than actual fragments of the rock itself, hanging visibly in the upper atmosphere, sometimes lit up by sunlight for many minutes after the event, drifting slowly and silently long after the noise has faded completely. This lingering trail is often the clearest visual evidence available before scientists gather more precise data from ground sensors and eyewitness reports. Scientists studying past airbursts rely heavily on eyewitness video and cell phone footage to reconstruct exactly what happened, since these events unfold too quickly and too unpredictably for scientific instruments alone to capture every detail. Dashboard cameras, security footage, and shaky phone videos have become genuinely valuable scientific tools, allowing researchers to measure the exact brightness, duration, and direction of a flash from dozens of separate angles at once, then combine that footage into a single, precise reconstruction of the event. An airburst like this leaves no crater and no deep scar in the Earth, and yet the sheer scale of energy it releases raises an obvious question. What happens when a rock 10 times larger than Chelyabinsk explodes above a place with no city, no witnesses, and only trees for hundreds of miles in every direction? On the morning of June 30th, 1908, in a remote stretch of Siberian forest called Tunguska, the sky exploded with a force that flattened an area larger than a major city, and almost nobody was there to see it happen. A local hunter camping many miles away later described being thrown from his chair by a blast of heat, convinced for a moment that the world itself was ending. There was no city nearby to count casualties, no camera to capture the flash, only a handful of scattered witnesses in one of the most isolated regions on the entire planet. The scale of destruction defies easy comparison. Roughly 80 million trees were knocked flat across an area of about 770 square miles, all of them pointing outward from a single central point, like matchsticks blown over by an invisible giant. Imagine every tree across an area larger than the city of Los Angeles, snapped or uprooted in the same direction within a matter of seconds. Scientists estimate the object responsible measured around 330 feet across, roughly the length of a football field, and released energy hundreds of times greater than the atomic bomb dropped on Hiroshima decades later. Here is the detail that turned Tunguska into a genuine scientific mystery. Despite the staggering destruction, no crater was ever found. Expeditions searching the site years later, delayed by the region's remoteness and years of political upheaval in Russia, expected to find a massive hole gouged into the earth. Instead, they found only flattened forest radiating outward from an empty centre, strong evidence that the object exploded high in the atmosphere rather than slamming directly into the ground, an airburst on a scale far beyond anything recorded since. For decades, this absence of a crater fueled wild theories, ranging from volcanic activity to, in the more imaginative corners of popular culture, alien spacecraft. The true explanation turned out to be simpler and in some ways more unsettling. A rock large enough to level a city arrived, detonated in the sky, and left behind devastation without a single fragment large enough to prove definitively what it actually was, until decades of careful scientific work pieced the story back together using nothing but the pattern of fallen trees. The first real scientific expedition did not reach the site until 1927, nearly 20 years after the blast, led by a Russian mineralogist named Leonid Kulik. He trekked for weeks through dense, roadless forest, expecting to find a crater filled with meteorite fragments worth studying. Instead, he found only that eerie radial pattern of fallen trees, still visible decades later, standing as the clearest physical evidence of what had actually happened that summer morning. Tunguska remains, to this day, the largest impact event recorded in human history, a stark reminder that the scale of destruction possible from space has already happened once, in living memory of recorded history, and simply happened to strike one of the emptiest places on Earth. If the exact same rock had arrived just a few hours later, as Earth continued rotating beneath it, that same devastating blast could have unfolded above a major city instead of an empty forest. That single detail, timing and geography, deciding the difference between an empty forest and a catastrophe, sits at the heart of every conversation scientists have today about tracking rocks before they arrive. For decades, the world's asteroid hunting telescopes focused their attention on the biggest, most dangerous rocks first, and there was good reason for that choice. An object wide enough to end civilization poses a threat so severe that finding every single one, even decades in advance, became an urgent global priority. Surveys succeeded remarkably well at this task. Astronomers now believe they have located the overwhelming majority of asteroids large enough to cause worldwide catastrophe, tracking their orbits carefully enough to rule out any collision for at least the next century. Smaller rocks tell a completely different story. A house-sized object, similar in scale to the rock that just broke this year's proximity record, reflects far less sunlight than a mountain-sized rock, making it dramatically harder to spot from far away. Existing telescopes, powerful as they are, were largely designed with bigger, brighter targets in mind. Finding something the size of a delivery truck often means waiting until it has drifted uncomfortably close to Earth, simply because that is the first point where enough sunlight bounces off its surface to register on a detector. Picture trying to spot a single black cat sitting in a dark room using only a dim flashlight from across the street. Now picture a car-sized cat instead, illuminated by the same weak flashlight, and the second one becomes visible from much farther away. Telescopes face this exact challenge every single night, and smaller rocks consistently lose that particular fight until they close enough distance for even a small amount of reflected sunlight to finally stand out. Sun glare compounds the entire problem. Rocks approaching from roughly the same direction as the sun in the sky hide inside its overwhelming brightness, invisible to ground-based telescopes for most of their approach. This exact blind spot let the Chelyabinsk rock arrive completely undetected back in 2013, and it remains one of the hardest gaps in the entire planetary defense system to close, since staring directly toward the sun would blind most telescopes outright. Engineers have started building solutions specifically aimed at this blind spot, including space-based telescopes positioned to scan the sky from angles impossible to achieve from the ground, catching rocks precisely in the glare that blinds observatories on Earth. These missions remain relatively new, expensive, and limited in number, meaning the vast majority of small rock detections still happen the same way this year's record breaker was found, discovered only in the final day or two before arrival. Cost explains much of this gap. A single space-based telescope can require years of development and hundreds of millions of dollars before it ever launches, while a ground-based observatory can often be built and operating within a fraction of that time and budget. Space agencies constantly weigh that trade-off, balancing the certainty of ground-based detection against the wider, glare-free view only a telescope in orbit can provide, and funding decisions made in budget meetings ultimately shape how much warning the entire planet receives before the next close call. This gap between how well we track the biggest threats and how poorly we track the smaller, more common ones defines the next frontier of planetary defense, and one particular new instrument is already starting to close that gap faster than anyone expected. High in the mountains of Chile, a telescope unlike anything built before began scanning the night sky, and within its very first 10 hours of operation, it discovered over 2,000 asteroids that had never been recorded by any observatory on Earth. Among that flood of new discoveries sat 7 near-Earth asteroids, rocks close enough to our planet's neighbourhood to actually matter for planetary defence. No previous telescope in history had ever found so much so quickly. This telescope belongs to a facility called the Vera Rubin Observatory, named for the astronomer whose work helped prove the existence of dark matter decades earlier. Its camera stands as the largest digital camera ever built for astronomy, capable of capturing an area of sky many times wider than the full moon in a single exposure. Instead of carefully studying one small patch of stars at a time, this instrument photographs enormous swaths of sky repeatedly, night after night, comparing each new image against the last to catch anything that moved. Think of older asteroid surveys as flashlights, carefully aimed at one spot at a time, patiently waiting for something to wander into view. This new observatory works more like a stadium-sized floodlight, illuminating almost the entire sky in wide, sweeping passes, catching motion across a scale no flashlight could ever match. What once took older telescopes months or years to accomplish, scanning the sky patch by patch, this single instrument now manages in a matter of nights. The impact on small, hard-to-find rocks could prove enormous. Objects the size of the one that just set this year's proximity record, previously detectable only in their final day or two before arrival, may soon be spotted weeks or even months in advance, simply because a telescope this sensitive and this fast can catch fainter, smaller targets far earlier in their approach. Astronomers expect the total number of known asteroids in our solar system to climb dramatically over just the next few years as this single facility works through its planned decade-long survey of the entire visible sky. More detections bring more responsibility. Every new asteroid discovered needs its orbit calculated, checked and monitored for years afterward, a task that grows heavier with every successful night of observation. Scientists are already building faster software and expanding international coordination specifically to handle the coming wave of data, aware that finding a rock is only useful if the world can process that information quickly enough to act on it. This shift did not happen by accident. Decades of planning, engineering and testing went into building a telescope capable of this kind of speed, involving thousands of scientists and engineers across multiple countries. Early test images released before the observatory reached full operation already stunned astronomers, revealing faint galaxies and moving objects that older instruments had simply never been sensitive enough to catch. What once felt like a distant, ambitious goal has now become an operating reality, reshaping expectations across the entire field of astronomy almost overnight. For the first time in the history of planetary defense, the challenge may soon shift from a shortage of detections to an overwhelming abundance of them, and how astronomers choose to handle that flood will shape how much warning humanity receives the next time something truly dangerous heads our way. The instant a telescope flags a new moving object, a very specific, very rehearsed process kicks into motion, one that has been refined over decades of practice. Nobody panics, nobody assumes the worst. Instead, a global community of astronomers begins quietly gathering the exact same three ingredients every single time: position, speed, and direction, treating each new discovery with the same careful process, regardless of how close or how large it initially appears. The first few hours matter most. A single observation only tells you where an object sat at one specific moment, nowhere near enough information to predict where it will travel next. A second observation, taken an hour or two later, suddenly reveals movement, a rough direction and speed. A third and a fourth and a fifth observation, gathered over the following hours, sharpen that rough sketch into an increasingly confident, mathematically precise path stretching both backward and forward through time. This process resembles connecting dots to reveal a hidden picture, except the dots keep arriving in real time, and the picture itself represents a rock hurtling through space at tens of thousands of miles per hour. Early on, the range of possible paths remains wide, sometimes wide enough to include a small, technically non-zero chance of impact somewhere on Earth. Astronomers never hide this uncertainty. They simply keep gathering data until that wide range narrows down to something extremely specific and confident. To communicate risk clearly to the public and to other scientists, astronomers rely on a tool called the Torino scale, created specifically to translate complicated orbital math into a simple number anyone can understand. It runs from 0, meaning no meaningful chance of impact, up to 10, reserved for a certain collision capable of global catastrophe. The overwhelming majority of newly discovered objects, including this year's record-setting flyby, get sorted quickly into that lowest category, confirmed safe well before they ever arrive. Reaching that safe conclusion takes real, careful work rather than a simple guess. Scientists compare new observations against thousands of other known orbits, run the numbers through multiple independent software systems to catch potential errors, and only declare an object safe once several separate calculations all agree. This layered, redundant process exists specifically to avoid both dangerous mistakes and unnecessary public alarm, since a false alarm can be almost as damaging to public trust as missing a real threat entirely. Experienced scientists in this field describe close passes like this one as routine rather than alarming, pointing out that car-sized objects drift between Earth and the Moon on a regular basis throughout any given year. That kind of calm, practiced confidence comes from decades spent watching thousands of similar objects arrive, get measured, and pass safely by, building a body of evidence that makes each new flyby easier to assess accurately and quickly than the one before it. For this particular rock, that entire process, from first detection to a confident, confirmed, safe verdict, unfolded within a single day. That kind of speed represents decades of accumulated expertise, working quietly and reliably in the background. Yet even the most confident, most reassuring verdict on a small rock like this one cannot fully answer the far bigger questions still waiting ahead. What happens on the rare occasion when the math reveals something the world genuinely needs to prepare for? On a September evening in 2022, a spacecraft roughly the size of a vending machine deliberately steered itself directly into an asteroid on purpose at more than 14,000 miles per hour. It was the most ambitious experiment ever attempted in the history of planetary defense, and for the first time, humanity actually changed the path of another world. The target was a small moon called Dimorphos, quietly orbiting a larger asteroid roughly half a mile across. Neither object threatened Earth in any way. Scientists chose this pair specifically because Dimorphos made the perfect test subject, small enough to nudge, safely far enough away that nothing could possibly go wrong, and orbiting its larger partner in a way that let telescopes on Earth measure the result with remarkable precision simply by timing how the shadow pattern between the two objects changed. The spacecraft carried no explosives, no rockets aimed at slowing it down, nothing dramatic in the traditional sense. It relied entirely on brute force, the raw momentum of a solid object slamming into another one, a strategy scientists call a kinetic impactor. Picture throwing a bowling ball at a shopping cart rolling slowly across a parking lot. The cart survives the hit fully intact, simply rolling off at a slightly new angle, nudged just enough by the transfer of momentum from the impact. Getting the spacecraft to hit its target required extraordinary precision. Dimorphos measures only about 520 feet across, a target roughly the width of 2 football fields, sitting more than 6 million miles from Earth at the moment of impact. The spacecraft navigated those final critical minutes entirely on its own, using an onboard camera and autonomous software to lock onto the asteroid and steer itself directly into the center, a feat of engineering that left almost no room for error given the distance involved. The results stunned even the scientists who designed the mission. Before impact, Dimorphos circled its larger partner once every 11 hours and 55 minutes. After the collision, that orbit shortened by 32 minutes, a change far larger than mission planners had dared to hope for. That single vending machine-sized spacecraft altered the orbit of an entire asteroid moon, proving conclusively that a well-timed nudge, delivered with enough advance warning, really can redirect a dangerous rock away from Earth. This success matters enormously for one simple reason: timing. A kinetic impactor works best when applied years, sometimes decades, before a rock's predicted arrival, since even a tiny nudge early in the journey grows into a massive shift in position by the time the rock would have reached Earth. Detect a dangerous rock early enough and a spacecraft barely larger than a refrigerator could be all it takes to steer disaster into empty space instead. That single fact reframes everything this entire story has been building toward. Every telescope hunting for faint dots of light, every hour spent calculating an orbit down to the mile, exists to buy exactly this kind of head start. Detection alone cannot stop a dangerous rock. It only earns humanity enough time to actually try. But deflecting a rock is only useful once you know it is coming, and that raises a much harder question, one that pushed engineers to attempt something even more delicate than a direct hit, flying close enough to study a dangerous rock without touching it at all. While one spacecraft proved humanity could shove an asteroid off course, another proved something almost the opposite, that a machine could thread the needle beside one without touching it at all. In July of this year, a small Japanese probe about the size of a refrigerator skimmed past an asteroid called Torifune at a distance of just 400 meters, roughly the length of 4 football fields laid end to end. No spacecraft in history had ever passed this close to an asteroid on purpose and lived to tell the story. The probe, named Hayabusa 2, had already spent years proving itself on an earlier mission, successfully landing on a different asteroid, collecting samples and returning them safely to Earth. Rather than retire after that achievement, mission planners sent it back out for an extended tour of the solar system, and this latest flyby became its boldest maneuver yet, a razor-thin pass designed specifically to test how precisely engineers could steer a spacecraft near a fast-moving, unpredictable target. This mission stretched the definition of what a single spacecraft could accomplish across its lifetime. Most probes complete one primary task and then power down or drift silently into the darkness once their fuel runs low. Hayabusa 2 kept working years past its original assignment, hopping from target to target, squeezing extra science out of a machine originally built with a single asteroid in mind. Engineers now treat it as a template for how future missions might extend their usefulness long after the headline achievement everyone remembers them for. Moving at more than 18,000 kilometers per hour, roughly 11,000 miles per hour, the probe had almost no room for error. A miscalculation of just a few dozen meters could have meant a catastrophic collision instead of a clean flyby. Engineers on the ground had planned for a slightly wider margin, expecting the probe to pass around 800 meters from the asteroid's center. Hayabusa 2 beat that target by a wide margin, coming in even closer than predicted, a result that thrilled the scientists tracking every second of the encounter from mission control back on Earth. Think of it like threading a bullet past a target the size of a house from a moving car without a single test run beforehand. Every angle, every burst of the probe's thrusters had to be calculated in advance and executed with almost no room to adjust once the maneuver began, since radio signals take minutes to travel between Earth and a spacecraft this far from home, far too slow to allow real-time correction during the closest seconds of approach. This kind of precision flying serves a purpose far beyond bragging rights. Every close pass beside a real asteroid teaches engineers exactly how a spacecraft can safely approach a fast-moving target, valuable practice for future missions that might one day need to fly alongside a genuinely dangerous rock, perhaps to study it up close, perhaps to prepare for a deflection attempt of its own. Skills tested on a harmless asteroid become the exact same skills a mission would rely on if a truly threatening rock ever needed a closer look before deflection. Missions like this remind us that humanity is no longer limited to watching asteroids pass by from a distance. We are now capable of chasing them down, flying beside them, and in some cases changing their paths entirely. Yet even with these victories, one particular rock, already circled on astronomers' calendars for years, is about to test every one of these hard-earned skills at once. Here is something that surprises most people the first time they hear it. Many scientists actively hope for asteroids to pass close to Earth. A close approach turns a distant theoretical rock into a rare, hands-on opportunity, a chance to study something that formed billions of years ago without spending the enormous time and money required to launch a dedicated mission all the way out to meet it. Radar tells much of this story. When an asteroid passes near enough to Earth, giant dish antennas on the ground can bounce powerful radio waves off its surface and capture the echo, essentially building a rough three-dimensional picture of a rock that would otherwise remain nothing more than a faint point of light. Scientists have used this technique to reveal asteroids shaped like spinning tops, others shaped like elongated peanuts, and some that turned out to be two separate rocks orbiting each other, invisible secrets that only a close pass close enough for radar could ever expose. Spacecraft missions push this curiosity even further. Rather than waiting for a rock to wander close to Earth, engineers now regularly send probes out to meet asteroids on their own turf, sometimes landing on the surface directly, sometimes scooping up small samples to bring home for study in laboratories far more sensitive than any instrument that could ever fit on a spacecraft. One such sample return mission successfully delivered material from an asteroid back to Earth, giving scientists their first direct, hands-on look at rock that had never touched our planet's atmosphere or surface before. These samples carry secrets far older than anything found naturally on Earth. Our planet's own surface constantly recycles itself through volcanic activity, erosion, and the slow grinding motion of tectonic plates, erasing most evidence of its earliest history. Asteroids, by contrast, often remain nearly frozen in time, chemically unchanged since the solar system's earliest days. Studying a piece of one is closer to reading an untouched diary from the birth of our entire solar system than to studying anything found here on Earth. Laboratories examining these samples have already turned up genuine surprises, including basic building blocks associated with life itself, preserved inside rock that never passed through an atmosphere thick enough to alter its chemistry. Findings like these fuel one of the biggest open questions in all of science: whether the raw ingredients for life on Earth actually arrived from space, carried here by rocks exactly like the ones drifting past our planet on an ordinary Tuesday. This is why a rock like the one that just broke this year's proximity record genuinely excited scientists rather than alarming them. Even a small, harmless flyby offers a brief, valuable window to point telescopes and radar dishes at a target that would otherwise remain far too faint and far too distant to study in any real detail. Every close pass becomes a small, free research opportunity, gone again within hours. Excitement like this makes perfect sense for a small, harmless rock passing safely by. But one particular object on the horizon, combines that same scientific opportunity with a scale and history that turns simple curiosity into something closer to global anticipation, an encounter astronomers have been counting down toward for over 2 decades, ever since the day it first earned a name that still makes headlines on its own. Somewhere on a calendar hanging in observatories around the world, one single date sits circled, highlighted, and counted down toward more carefully than almost any other astronomical event this century. It falls on a Friday in April of 2029, still years away, and yet scientists have already been preparing for it for more than 2 decades. Every rock discussed so far in this story, including this year's record-setting flyby, exists in the shadow of what happens on that single Friday. The rock responsible for all this attention was first spotted in June of 2004, drifting through the darkness on a completely unremarkable night, indistinguishable at first glance from thousands of other faint dots astronomers catalogue every year. Early calculations of its orbit, however, revealed something that made an entire room of scientists sit up straight, a genuine non-zero chance that this particular rock could strike Earth decades later. For a brief, tense period, this newly discovered object became the single most concerning asteroid ever tracked by modern astronomy. Additional observations eventually ruled out any chance of impact for at least the next century, and the panic faded as quickly as it had arrived. What remained, though, was something far rarer than a genuine threat, a rock large enough to matter, on a path that would still bring it remarkably, safely close to Earth, at a distance far tighter than almost anything else its size has ever managed, without actually striking the planet. That ruling out process took real time and real work. Astronomers spent months gathering additional observations, refining the rock's orbit with every new data point, slowly shrinking a wide range of possible futures down to a single confident path. Only after that painstaking process did officials feel comfortable enough to lower the object's threat rating publicly, a decision that made headlines around the world and offered genuine relief to scientists who had spent those months living with real uncertainty about a rock this size sets this object apart from everything covered earlier in this story. Where this year's record breaker measured only a few dozen feet across, this rock stretches over 1,200 feet wide, closer in scale to a skyscraper lying on its side than to a delivery truck. An object this large passing anywhere near Earth would normally stay hundreds of thousands, even millions of miles away. This one will not. When it arrives in 2029, it will pass closer to Earth than many satellites that orbit our planet every single day, a combination of size and proximity that has never been recorded for an object this large in the entire history of organised asteroid tracking. Scientists describe encounters like this as happening perhaps once every few thousand years, an extraordinarily rare alignment of size, distance and timing that will not repeat again for generations. Everything you have learned so far, the telescopes racing against faint light, the careful math behind every safe verdict, the missions built to nudge dangerous rocks away, all of it converges on this single upcoming event. And the story of exactly why this rock earned its unforgettable nickname begins with the fear it once inspired, before the math finally proved that fear wrong, years before anyone could relax enough to look forward to the encounter instead of dreading it. Every dangerous-sounding object deserves a name that matches the fear it once inspired, and astronomers chose this one with real intention. They named the rock Apophis, after an ancient Egyptian deity representing chaos, darkness and destruction, a serpent said to battle the sun itself each night, in an endless attempt to plunge the world into permanent shadow. For a rock that briefly ranked as the most threatening object ever tracked, the name fit with unsettling precision. The choice was not random. Astronomers often draw asteroid names from mythology, but this particular selection carried a knowing wink, a nod to just how seriously scientists took the early threat calculations. Naming a potentially dangerous rock after a god of chaos and darkness reflected genuine concern from a community that does not frighten easily. People who spend their careers calmly reassuring the public about far less threatening objects almost every single week. That reputation stuck long after the danger itself faded. Even years after additional observations ruled out any realistic chance of impact, the nickname God of Chaos remained permanently attached to the rock, appearing in nearly every headline, documentary, and public conversation about it since. Names like this carry weight far beyond their scientific accuracy, shaping how an entire generation of students, journalists, and curious sky watchers first learn about a rock that, despite its terrifying introduction, poses no danger at all. Popular culture only reinforced that impression. Documentary crews, news anchors, and science communicators reached for the same dramatic language again and again, framing every update about the rock's orbit as a chapter in an ongoing battle between doom and reassurance. Even now, mentioning the name alone is often enough to spark a flicker of unease in people who half remember hearing about a killer asteroid years earlier, long before most of them ever learned the actual far calmer ending to that particular story. Understanding why the early scare happened at all reveals something important about how asteroid tracking actually works. When a rock is first discovered, astronomers only have a small handful of observations to work with, nowhere near enough to calculate a precise, confident path. That early uncertainty naturally includes a wide range of possible outcomes, some of them alarming, purely because the mathematics has not yet had enough data to narrow itself down. Apophis briefly fell into that uncertain range simply because scientists were being appropriately cautious, with incomplete information, exactly the same caution applied to every new discovery before enough data arrives to settle the question. This same pattern plays out, in miniature, every single time a new rock gets discovered, including the record-setting flyby that opened this entire story. Early estimates always carry more uncertainty than later ones, and a healthy dose of caution in those first hours protects the public far better than false confidence ever could. Apophis simply represents the most dramatic example of that pattern, playing out on the largest possible stage, a single early estimate turning an ordinary discovery into a genuine global headline almost overnight. Today, that same rock, once feared as a symbol of chaos, is treated as one of the most anticipated scientific opportunities of the decade, and the reason for that complete reversal comes down to a single, remarkable detail about how close it will actually come. Every other rock in this entire story has shared one quiet detail in common: invisibility. Even the record-breaking flyby that opened this series stayed completely hidden from ordinary eyes, requiring a telescope and exact timing just to catch a faint glimpse. Apophis breaks that pattern entirely. When it arrives in April of 2029, people across parts of Europe, Africa, and the Middle East will be able to walk outside, look up, and see it drifting across the sky using nothing but their own eyes. This alone makes the encounter almost unprecedented. Asteroids large enough to see without equipment almost never pass close enough to Earth to actually become visible, since brightness depends heavily on both size and distance working together. A rock has to thread an extremely narrow needle, big enough to reflect meaningful sunlight, yet close enough for that light to actually reach a human eye without the help of a lens. Apophis threads that needle almost perfectly. Picture a point of light crossing the sky steadily over the course of an hour, moving noticeably against the fixed background of stars, unlike anything most people have ever witnessed with their own eyes. Satellites cross the sky quickly, gone within minutes. Meteors flash and vanish in a single second. Apophis will move slowly and deliberately enough for entire crowds to track its path in real time. A rare, unhurried spectacle rather than a blink and miss it flash. Scientists expect the asteroid to shine at a brightness comparable to some of the fainter stars visible to the naked eye, easily bright enough to spot from areas without heavy light pollution. Cities with bright skylines will likely wash out the view entirely, but rural areas and dark sky locations across the flyby's visible path should offer a genuinely striking sight, a slow, moving point of light crossing overhead in complete silence. Timing plays a critical role in whether any given viewer actually gets to see it. The asteroid brightens dramatically only in the hours immediately surrounding its closest approach, meaning observers need to be looking at almost exactly the right moment, in almost exactly the right location, under a clear enough sky to actually spot something this faint. Miss that narrow window, and the rock fades back into ordinary telescope territory within a day, invisible again to anyone without proper equipment. This visibility transforms Apophis from a purely scientific event into a shared public spectacle, likely to draw crowds outdoors specifically to watch. Cameras and telescopes pointed skyward across 3 continents simultaneously. Astronomers anticipate coordinated public viewing events, live broadcasts and packed observatories, treating the flyby less like a routine scientific milestone and more like a rare celestial festival that will not repeat again for generations, a once-in-a-lifetime chance for millions of people to watch a genuine asteroid with nothing more than patience and a clear sky. Seeing a rock this size with nothing but your own eyes drives home a scale that numbers alone rarely capture. But brightness only tells part of the story, because the true significance of this flyby comes down to exactly how large this object actually is, compared to everything else you've already learned about in this series, a comparison that turns an abstract number into something genuinely hard to fully picture. Numbers alone rarely capture scale the way a direct comparison can, so here is one worth sitting with. The rock that opened this entire story, the one that set this year's proximity record, measured somewhere between 20 and 50 feet across, roughly the size of a delivery truck. Apophis measures over 1,200 feet across. Lined up side by side, you could fit more than 20 delivery trucks end to end, and still fall short of matching this single object's width. Height offers another way to picture it. A typical 30-story skyscraper stands somewhere around 350 feet tall. Apophis stretches more than 3 times that height, laid on its side and hurtling through space at tens of thousands of miles per hour. Picture the tallest building in your city, then imagine 3 of them stacked end to end, tumbling silently through the darkness of space, spinning slowly enough that its shape shifts and changes with every hour of the flyby, and you start to approach the true scale of this particular rock. Mass grows even faster than size, since volume scales with the cube of an object's width rather than in a straight line. Apophis outweighs this year's record breaker by a factor closer to several million. Every single kilogram of that mass carries kinetic energy proportional to its weight and its speed, meaning an object this size striking Earth would release energy on a scale utterly disconnected from anything discussed earlier in this story. Even a fraction of that energy, released in the wrong place, could reshape a region the size of a small country. This is precisely why scientists devoted decades of careful observation specifically to this one rock, rather than treating it the same way they treat the countless smaller objects that pass by every single week. Objects the size of this year's flyby arrive constantly and rarely earn more than a footnote in scientific records. Objects the size of Apophis arrive on a completely different timescale, some estimates suggesting a close past this significant for an object this large happens only once every several thousand years. Consider the Empire State Building as one more anchor point for this comparison. That structure stands roughly 1,250 feet tall from base to antenna, meaning Apophis, at over 1,200 feet across, comes close to matching one of the tallest buildings ever constructed by humans, except this version tumbles slowly through space, spinning on its own axis every several hours, an entire building-sized world drifting silently through the darkness between planets. Rarity like that explains the intensity of scientific interest surrounding the 2029 flyby. This encounter represents a genuinely unique opportunity to study an object of true civilization-scale consequence, up close, safely, and without any risk of impact. A combination that may not occur again within the lifetime of anyone reading or listening to this sentence. Telescopes, radar dishes, and possibly even spacecraft are already being positioned years in advance, all aimed at squeezing every possible detail out of a window that will close again almost as quickly as it opens. Size this extreme raises an unavoidable question, one that pushes beyond simple curiosity into genuine physics. What actually happens when something this massive passes close enough to Earth for our planet's own gravity to reach out and touch it, close enough to leave a lasting mark on the rock itself rather than the other way around? Gravity is not a one-way conversation. Every time a massive object drifts near a planet, the planet pulls on it, and the object pulls back, however faintly, on the planet. For most asteroids, this exchange barely registers, a gentle tug too small to matter. Apophis is large enough, and will pass close enough, for that exchange to actually leave a mark, reshaping the rock itself in ways scientists have never been able to observe this clearly before. The effect responsible for this is called a tidal force, the same basic physics that pulls ocean water toward the moon here on Earth, creating the tides that shape entire coastlines twice a day. When Apophis sweeps past our planet, Earth's gravity will pull harder on the side of the rock facing us than on the side facing away, since gravity weakens with distance even across an object only a few hundred feet wide. That difference in pull creates a subtle but real stretching force across the asteroid's structure. Scientists expect this stretching to trigger something remarkable: small landslides and shifting rubble across the surface of the asteroid itself, similar to how a gentle earthquake might loosen rocks on a steep hillside here on Earth. Apophis, like many asteroids its size, behaves more like a loosely packed rubble pile than one solid, unbroken chunk of stone, boulders and dust held together mainly by their own weak gravity, rather than any real structural strength, making it especially sensitive to an outside tug this significant. Think of it like shaking a jar filled loosely with gravel rather than striking a single solid rock with a hammer. The gravel inside the jar shifts, resettles, and finds a new arrangement without the jar itself ever breaking apart. Apophis is expected to behave in a similar way, its loose surface material sliding and resettling under Earth's pull, potentially exposing fresh material that has never been touched by direct sunlight. Material scientists are eager to study the moment it becomes visible. Rotation offers another visible clue. Apophis currently tumbles through space with a measurable spin, completing one full rotation every several hours. Earth's gravity during the 2029 flyby is expected to alter that spin rate, speeding it up or slowing it down depending on the rock's exact orientation during closest approach. Scientists plan to measure this change precisely, using it as a rare, real-world experiment in exactly how planetary gravity interacts with a rubble pile object of this size. This encounter offers something almost impossible to arrange through any other means, a natural experiment on a scale no laboratory or spacecraft mission could ever replicate. Watching Earth's gravity physically reshape an object over 1,000 feet wide in real time, using telescopes and radar already pointed and waiting, will teach scientists more about asteroid structure than decades of distant observation ever could. Insight that could directly improve how future deflection missions are planned and executed. Yet this same gravitational tug that fascinates scientists also raises a far more unsettling possibility, one that has nothing to do with this particular safe flyby, and everything to do with what might happen the next time a large rock passes through the exact same narrow patch of space. A possibility with a name of its own, and a reputation for turning safe passes into future problems. Somewhere in the empty space near Earth, invisible and impossible to see with any telescope, exist tiny regions scientists call gravitational keyholes. Picture them as small, specific windows floating in space, each one only a few miles wide, positioned along an asteroid's path. Pass through open space, and nothing unusual happens. Pass directly through one of these narrow windows, and Earth's gravity bends an asteroid's future path just enough to set up a genuine impact on a later orbit, sometimes years or even decades down the line, all from a difference in position too small to notice with the naked eye. Here is what makes keyholes so strange to think about. A keyhole only matters if an asteroid happens to pass through that exact tiny patch of space during a close flyby. Miss it by even a small margin, roughly the width of a keyhole itself, often just a handful of miles, and the future path bends in a completely different, harmless direction instead. Scientists first identify these keyholes by running an asteroid's orbit forward through powerful computer simulations, testing thousands of slightly different possible paths based on the small uncertainties still present in any set of observations. Wherever a cluster of those simulated paths leads toward a future collision, that patch of space earns a keyhole label and gets watched with extra scrutiny during every subsequent close approach, long before the asteroid itself ever gets anywhere near it. Apophis briefly worried scientists precisely because of this concept. During the early uncertain years right after its discovery, calculations could not yet rule out the possibility that its 2029 flyby might send it drifting directly through one of these small keyholes, setting up a possible impact 7 years later in 2036. This scenario captured global attention for years, driving intense research specifically aimed at ruling the possibility in or out with total confidence. Additional years of careful tracking eventually solved the puzzle completely. Refined measurements of the asteroid's exact position, gathered using both traditional telescopes and precise radar observations, narrowed its predicted path enough to confirm that Apophis will safely miss every known keyhole associated with a future impact. The 2036 scenario, once a genuine source of scientific concern, has since been fully ruled out, closing that particular chapter of uncertainty for good, a resolution scientists announced only after years of painstaking, repeated observation. Keyholes reveal something important about how close approaches actually work. A single safe flyby, even one that misses Earth by a wide, comfortable margin, does not automatically guarantee safety on every future pass. Small, invisible regions scattered along an orbit can quietly turn a routine flyby into a setup for something far more serious down the line, which is exactly why scientists keep tracking objects like Apophis for years after the immediate danger has technically passed, refining every observation until the last shred of doubt disappears. Understanding keyholes changes how you should think about every close call in this entire story. A safe distance today says nothing certain about tomorrow, and that uncomfortable truth is precisely why global tracking networks never fully stop watching, even after a rock has been declared safe, treating every confirmed close approach as the beginning of years of continued observation rather than the end of the story. Every rock discussed so far in this story ended safely. A flyby, a close call, a scientific curiosity rather than a genuine emergency. It is worth pausing here to walk through what would actually happen if that pattern ever broke. If a rock large enough to matter were discovered only hours before impact instead of years. Scientists have run this exact scenario many times, treating preparation as something that depends entirely on having a plan already worked out before it is ever needed. The first hours would look almost identical to every discovery already covered in this story. A telescope flags a moving object. Astronomers scramble to confirm it, calculate its path, and estimate its size. The difference in this scenario comes from what those numbers reveal: a genuine, confirmed collision course, with a rock large enough to cause real damage on the ground, and a countdown measured in hours rather than years. At that point, deflection stops being an option entirely. Every method scientists have developed, from a kinetic impactor like the one that successfully nudged Dimorphos, to slower techniques that rely on years of gentle gravitational tugging, requires far more lead time than a single day could ever provide. With hours instead of years on the clock, the entire response shifts away from stopping the rock and toward protecting the people standing in its path. Emergency planners have already mapped out exactly what that shift looks like. Scientists would calculate the most likely impact zone as precisely as possible, narrowing it down from an entire country to a specific region, and eventually to a much smaller area as final observations refine the prediction. Local authorities would then face an urgent, narrow window to evacuate that zone, shelter residents outside the blast radius, and warn coastal areas if the impact site sits near open water, since a strike close to shore can trigger dangerous waves stretching for miles along the coastline. Every level of government in the affected region would need to move in near-perfect coordination, something that rarely happens smoothly even during far more familiar disasters like hurricanes or wildfires, events that typically arrive with days of advance warning rather than mere hours. Officials would be forced to compress an entire emergency response, usually spread across a week or more of preparation, into a fraction of that time, all while keeping the public informed without triggering panic that could slow the evacuation itself. Communication becomes the single most critical tool in a scenario like this. International agencies have practiced exactly this kind of rapid alert system, running simulated exercises specifically designed to test how quickly a warning can travel from a telescope on a mountaintop to an emergency broadcast reaching millions of people. These drills have exposed real weaknesses, gaps in translation, delays in official confirmation, confusion between overlapping agencies, each one a lesson quietly folded back into the next version of the plan. This scenario remains thankfully hypothetical for every rock covered in this entire story. Yet hypothetical is not the same as impossible, and the very existence of a rehearsed, detailed plan raises an uncomfortable follow-up question. Exactly how many rocks capable of triggering this scenario are still out there, completely undiscovered, right now, drifting closer with every passing year while no telescope on Earth has yet noticed them? No single country owns the sky, and no single country can protect Earth from a dangerous asteroid alone. This simple reality led scientists and governments to build something unusual in the world of international cooperation, a genuine, functioning global network specifically dedicated to sharing asteroid data instantly, freely, and without the political friction that slows down almost every other form of international coordination, spanning dozens of countries that otherwise rarely agree on anything at all. This network operates under an organisation called the International Asteroid Warning Network, endorsed by the United Nations specifically to make sure a life-threatening discovery never gets delayed by bureaucracy, competition, or simple miscommunication between countries. The moment any observatory anywhere in the world spots a new object worth watching, that data flows immediately into a shared, publicly accessible system, available to scientists, space agencies, and other observatories on every continent within minutes rather than days. Alongside that data-sharing network sits a second, closely related group focused specifically on response rather than detection, made up of space agencies capable of actually mounting a deflection mission if one were ever needed. These two groups work in constant contact with each other, one watching the sky for new threats, the other quietly maintaining the technical readiness to act the moment a genuine threat gets confirmed, an arrangement built specifically so that detection and response never end up working in isolation from each other. This system works because everyone involved agreed, early on, to treat asteroid tracking differently than the almost every other scientific field. Discoveries in most areas of science come with competition, researchers racing to publish first, guarding data until their own analysis is complete. Asteroid tracking abandoned that model almost entirely. A telescope in Chile shares its raw data with a telescope in Hawaii within the same night. No delay, no exclusivity, no scientific rivalry standing in the way of a potentially urgent calculation. Think of it like a neighbourhood watch that spans the entire planet, where every single participant agrees in advance to shout a warning the instant something looks wrong, regardless of who spotted it first or which country gets credit for the discovery. That shared, almost instinctive cooperation explains how a rock discovered at a small observatory in the Canary Islands, exactly like the one that opened this entire story, can be confirmed, tracked, and cleared as safe by telescopes on completely different continents within a single day. Beyond simple data sharing, this same network runs regular international exercises, simulating exactly how a genuine warning would move through the system if a dangerous rock were ever actually found on a collision course. These drills involve real space agencies, real emergency planners, and real government representatives, all practicing the exact handoff from initial discovery to public warning long before any real emergency ever forces that system into action for the first time, revealing weak points in communication that get quietly fixed before they can ever matter for real. None of this cooperation happened automatically. It took decades of deliberate work, treaties, shared funding agreements, and countless meetings between scientists who otherwise might never have collaborated, all built around one shared, uncomfortable acknowledgement that a rock from space does not check passports before it decides where to strike, a fact that turned old rivalries into something closer to a shared planetary responsibility. Ask any planetary defense scientist their honest opinion on this question, and you will get a surprisingly direct answer. When it comes to the truly massive rocks, the ones large enough to threaten civilization itself, astronomers believe they have found the overwhelming majority already, but shrink the size down toward anything resembling this year's record breaker, and that same confidence collapses almost completely, replaced by a far more honest, far more uncertain shrug. Large asteroids earn attention first for a simple reason: math. An object wide enough to end civilization reflects enormous amounts of sunlight, making it relatively easy to spot even from staggering distances. Decades of dedicated survey work have located roughly 90% of asteroids in that largest, most catastrophic size category, tracking their orbits carefully enough to confirm none of them poses any realistic threat for at least the next century. This represents one of the genuine triumphs of modern astronomy, a problem capable of ending civilization, largely solved through patient, careful observation. Move down to house-sized rocks, similar in scale to the one that opened this entire story, and the picture changes dramatically. Astronomers estimate they have identified only a small fraction of objects this size currently drifting through Earth's neighbourhood, likely somewhere in the range of a few percent of the total population believed to actually exist. The vast majority remain completely unknown, too small, too dark, and too faint for existing telescopes to catch, until they happen to wander unusually close. Somewhere in between these two extremes sits a middle category, rocks a few hundred feet across, large enough to level a small city if they struck the wrong location, yet still small and dark enough to slip past most existing surveys undetected. Astronomers consider this middle category the single greatest remaining gap in global asteroid tracking. Too big to ignore, too faint to reliably catch, and numerous enough that a genuine surprise from this size range remains a real, if uncommon, possibility. This gap is not a failure of effort. It reflects the sheer scale of the challenge involved. Millions of rocks this size likely populate the space between Earth and the asteroid belt, each one requiring an enormous amount of luck, timing, and reflected sunlight to ever become visible from the ground. Finding every single one would require telescope coverage far beyond anything currently operating, a gap that new instruments like the Rubin Observatory are only just beginning to close, one wide, sweeping scan of the sky at a time. Put simply, the biggest, most catastrophic threats sit largely mapped and monitored, while the smaller, more common category, still large enough to level a city or shatter windows for miles, remains mostly invisible until the final hours before arrival. This is precisely why a rock like this year's record breaker could appear from nowhere and reach Earth in under a day, and why similar surprises will likely keep happening for years to come, even as detection technology continues improving. Somewhere in that vast, uncounted population of undiscovered rocks sits the ordinary comparison every close call eventually returns to the single most destructive impact this planet has ever recorded, one that happened long before any telescope existed to give humanity even a moment of warning, and whose scale still shapes how scientists imagine the very worst-case scenario today. 66 million years ago, long before mountains, oceans, and continents settled into the shapes we recognize today, a rock roughly 7.5 miles wide slammed into what is now the coast of Mexico at a speed exceeding 40,000 miles per hour. In a single instant, the age of the dinosaurs, a chapter of Earth's history stretching back over 150 million years, came to a permanent, catastrophic end. The impact itself defies ordinary description. Energy equivalent to billions of atomic bombs detonated all at once tore a crater over 90 miles wide into the crust of the planet, a scar so massive it remains detectable today only through satellite imaging and careful geological surveys, buried beneath layers of rock and ocean sediment accumulated over tens of millions of years. Within seconds of impact, the surrounding region for hundreds of miles simply ceased to exist in any recognizable form. Scientists only pieced this story together relatively recently, using clues buried far from the impact site itself. A thin layer of unusual metal-rich clay, found in rock formations scattered across the entire planet, first tipped researchers off that something extraordinary had happened at exactly this moment in Earth's history. That single globally distributed layer, barely thicker than a coin in most places, ultimately led scientists straight to a buried crater off the coast of Mexico, confirming a theory that once sounded almost too dramatic to take seriously. What followed the initial blast proved even more devastating than the impact itself. Massive amounts of pulverized rock and dust launched high into the atmosphere, some of it circling the entire globe within hours. Wildfires ignited across enormous stretches of forest as superheated debris rained back down from the sky. Within months, that dust cloud blocked enough sunlight to plunge the planet into a prolonged artificial winter, collapsing plant growth across nearly every ecosystem on Earth and starving the food chain from the bottom up. Ocean life suffered just as severely as anything living on land. Massive waves, triggered by the impact itself, tore through coastlines thousands of miles from the crater. Sunlight blocked by drifting ash-starved microscopic ocean plants first, collapsing an entire food chain that stretched all the way up to the largest marine predators of that era. Roughly 3/4 of all species alive at that moment vanished within a relatively short window afterward, an extinction event so severe it remains one of only 5 such mass extinctions recorded in the entire history of life on this planet. Dinosaurs, having dominated Earth for well over 100 million years, disappeared almost entirely, clearing space for small, previously overshadowed mammals to eventually rise, diversify, and tens of millions of years later, evolve into the very species writing and reading this sentence today. Compare this to every other event covered throughout this entire story, and the scale becomes almost impossible to process honestly. Chelyabinsk shattered windows across a single region. Tunguska flattened a forest larger than a major city. The Chicxulub impact reshaped the trajectory of life on an entire planet, ending one era completely and setting the stage, quite literally, for humanity's own eventual existence. This single ancient event explains, more than any statistic or safety verdict discussed so far, exactly why scientists dedicate entire careers to tracking rocks far smaller and far less dangerous than this one. The math surrounding that catastrophe never fully leaves the room, quietly shaping every telescope built, every warning system designed, and every safe verdict delivered about a much smaller rock passing harmlessly by. Stack every single object covered throughout this entire story, side by side, and a strange, almost reassuring pattern emerges. This year's record-breaking flyby, small enough to fit on a city street. Chelyabinsk, big enough to shatter windows across a region. Tunguska, big enough to flatten a forest the size of a major city. Apophis, big enough to rank among the most closely watched objects in the solar system. And finally, the Chicxulub impactor, big enough to end an entire geological era. Each step up this ladder represents an enormous, almost incomprehensible jump in scale. Here's the reassuring part hidden inside all that destruction. Objects capable of a Chicxulub-level catastrophe are rare almost beyond imagination, striking Earth on a timescale measured in tens of millions of years rather than centuries or decades. Astronomers have identified nearly every object in that extreme size category currently orbiting anywhere near Earth, and not a single one shows any realistic chance of impact for the foreseeable future. The worst-case scenario in this entire story remains, for all practical purposes, solved. That confidence did not arrive overnight. It took decades of dedicated survey work, telescope after telescope scanning the same regions of sky year after year, cross-checking results against each other until the scientific community reached genuine consensus. Very few problems this large, capable of ending civilization outright, have ever been addressed this thoroughly, and the story of how astronomers reached that point deserves real recognition alongside every close call and near-miss covered earlier in this series. Smaller events occupy a very different position on that same scale. Tunguska-sized impacts, capable of flattening an area the size of a major city, occur on a timescale closer to once every few centuries, rare enough to feel abstract, yet common enough that another one will almost certainly happen again someday. Chelyabinsk-sized events, capable of shattering windows across an entire region, happen far more frequently, likely once every few decades somewhere on the planet, though most occur harmlessly over oceans or uninhabited land where nobody notices at all. This sliding scale explains exactly why scientists focus their limited resources where they matter most. Chasing down every single small, harmless rock passing near Earth would waste enormous time and money better spent elsewhere. Instead, the entire planetary defense community concentrates its effort on closing the gap in the middle, rocks large enough to genuinely hurt a city, yet still small and faint enough to slip past current detection until the final hours. Every telescope, every international agreement, every deflection mission tested so far exists specifically to shrink that dangerous middle category down toward nothing, the same way the largest, most catastrophic threats have already been almost entirely accounted for. Progress here does not happen through dramatic headlines or sudden breakthroughs. It happens through decades of patient, unglamorous work, one new telescope, one refined orbit, one successful test mission at a time. Understanding this entire scale, from a harmless truck-sized rock to an extinction-level impactor, changes how every future headline about a close asteroid pass should actually land. The question worth asking is never simply how close, it is always how big, and exactly where that particular rock falls on a ladder stretching from a shattered window all the way up to the end of an entire era. Every tool covered throughout this entire story, telescopes scanning the darkness, spacecraft nudging asteroids off course, international networks sharing data in real time, represents where planetary defense stands today. None of it represents where the field is headed next. Scientists and engineers are already designing the next generation of tools specifically built to close the gaps this story has spent so much time exploring. Space-based detection sits at the top of that list. Ground telescopes, however powerful, remain permanently blind to rocks approaching from the direction of the Sun, the exact blind spot that let the Chelyabinsk rock arrive without warning. New missions, positioned in orbit rather than bolted to a mountaintop, aim to scan the sky from angles no ground-based observatory could ever achieve, catching rocks hiding in glare that has concealed dangerous objects for as long as humans have been watching the sky. Infrared detection offers another promising path forward. Many asteroids that reflect almost no visible light still radiate detectable heat, warmed slightly by distant sunlight even while remaining nearly invisible to a traditional camera. Telescopes tuned specifically to sense that faint heat signature can spot dark, dangerous rocks that ordinary optical surveys would completely miss, effectively adding an entirely new sense to humanity's collective ability to watch the sky, catching precisely the objects most likely to slip through every other existing method of detection. Detection speed continues accelerating as well. The Rubin Observatory, already reshaping how quickly astronomers catalogue new objects, represents just the beginning of a broader shift toward wide, fast, automated sky surveys. Future instruments promise to scan even larger sections of sky, even faster, potentially shrinking the typical warning window for a rock like this year's record breaker from less than a day down to weeks or even months, transforming a frantic scramble into a calm, well-planned response instead of a last-minute race against the clock. Deflection technology keeps advancing too, building directly on lessons learned from the successful kinetic impactor mission described earlier in this story. Engineers are studying additional techniques, including spacecraft designed to hover near a threatening asteroid for years, using nothing more than their own gentle gravitational pull to slowly tug the rock onto a safer path over time. Slower than a direct collision, this method offers something a sudden impact cannot: precise, gradual control over exactly how much a dangerous rock's path actually shifts, useful for situations where a sharp, sudden nudge might risk breaking a fragile rubble pile apart entirely. None of these advances happen in isolation. Every new telescope, every refined deflection technique, every strengthened international agreement builds directly on knowledge gathered from ordinary flybys, just like the one that opened this entire story. Even a small, harmless rock passing safely by contributes real, usable data, sharpening the tools scientists will eventually need for something far more serious. Proof that curiosity about a truck-sized rock and preparation for something civilization-threatening ultimately draw from the exact same well of knowledge. The story of planetary defense remains, in many ways, still being written, one flyby, one mission, and one international exercise at a time. And that brings this particular chapter of the story back to exactly where it began, with a simple, quiet question about which rock might claim the next record, and how much warning humanity will actually get before it does. Somewhere between Earth and the asteroid belt right now, a rock is quietly drifting closer, completely unaware, in the way only a lifeless piece of stone can be, that it may eventually claim the exact record broken by the flyby that opened this entire story. It has no name yet. No telescope has spotted it. No astronomer has calculated its path. Yet based on everything covered across this series, its eventual discovery feels less like a possibility and more like a mathematical certainty. Every single year, dozens of similar rocks slip past Earth within a lunar distance, and the numbers suggest this pattern will only continue. As detection technology keeps improving, telescopes like the Rubin Observatory will likely catch smaller, closer, faster objects than anything discussed in this story, meaning new proximity records will probably fall again within the next few years, perhaps even faster than most people expect. This year's record breaker earned its title only by being the closest object tracked so far. Nothing about that title guarantees permanence. Somewhere along that same timeline sits Apophis, still years away, still the single most anticipated encounter this series has covered. Between now and that Friday in April, more record-breaking flybys will almost certainly happen. More faint smudges of light will get discovered with barely a day to spare, and more ordinary nights will pass with nobody on the ground ever realizing how close another quiet, harmless rock came to grazing their planet. That is precisely the point worth carrying forward from everything covered in this series. Records like this exist only as snapshots of our current detection ability, not as some kind of natural ceiling on how close a rock can actually come. Every year, telescopes get sharper, surveys get faster, and the population of known asteroids keeps growing, which means the very definition of record setting keeps shifting along with it. Think back to where this story began. A faint smudge of light on a telescope screen in the Canary Islands, spotted less than a day before a truck-sized rock swept past Earth, closer than any object tracked in 2026. That single, quiet moment connects directly to everything that followed: satellites and gravity, Chelyabinsk and Tunguska, a mission that nudged an asteroid off course, a giant rock once feared as a symbol of chaos, and finally, the ancient impact that ended an entire era and cleared the way for humanity to exist at all. None of these stories exist in isolation. Every close pass, every safe verdict, every rare, unsettling exception builds toward the same quiet, ongoing project, watching the sky closely enough that humanity never gets caught completely by surprise. That project has no true finish line. It simply continues, one telescope, one discovery, and one carefully calculated orbit at a time. A quiet, constant vigilance most people never think about until a headline briefly pulls their eyes back up toward the sky. The next record-breaking flyby is already out there somewhere, drifting silently through the dark, waiting for its own turn under a telescope's watchful eye. When it arrives, the process will look almost exactly like the one that opened this story. A faint smudge of light, a race against the clock, and, once again, a planet that never even noticed how close it came, still turning quietly beneath a sky far busier than it has ever looked.